Okay, all right, let's get started. So this is going to be the first tutorial for assignment 3. And assignment 3 usually used to be about speech recognition in the previous years. This year has changed a bit, so there's a little bit more natural language understanding. There's a little bit more, I think it's a little easier than it used to be in previous years, which is a good thing. So maybe I don't actually have a lot of things planned out. I can just go through the assignment handout one question at a time and see exactly if you have any concerns for each part. If not, we can talk about speech recognition like I did in the previous half. I can talk about speech recognition as a general problem in machine learning and see if you guys are interested in that. We can talk about that. It's not going to be that relevant to the assignment itself. But if you're really interested in speech recognition as a research field, or if you want to do a master's or a PhD later on in machine learning, this might be of relevance. Okay. So should we take up questions for assignment 3? If there's any questions for assignment 3 first? Or should we just do like a more general introduction to speech recognition first? Whatever you guys prefer. I mean, should we just start off with speech recognition as an introduction then? Okay, so let me just talk about speech recognition in general. There used to be actually quite a hard problem before. Like before we had all these really good. So now we have SpeechBrain. I think this is going to be from the SpeechBrain tutorial section. Yeah, speech recognition from scratch. Okay. So this one is from SpeechBrain, which is essentially a really nice framework for doing speech recognition and also a lot of other things in speech, like text-to-speech, and there's a couple of other problems as well. But I'll mostly focus on speech recognition because this is something I've done myself when I was working at a startup back in I'm growing old. Back in 2016 or 2018, I forget now. Yeah, I think I worked there for 2 years, from 2016 to 2018. This is the thing I was doing. I was working on speech recognition. And back then, there was no SpeechBrain, right? So it was a lot harder for me to actually figure out these different moving parts. And you kind of understand why that's the case by the end of this lecture, okay? For speech recognition, usually there's not just one big model, but there's a bunch of different moving pieces. And then you have this one big pipeline that you have at the end that hopefully can transcribe speech in different settings, okay? There's a lot of different sort of variations to this problem, but essentially at the core of this is going to be 3 steps, okay? The first step is going to be extracting the features from the actual audio files. So let's just say you speak something in an audio file, you record that file, right? That's going to be the data we use, right? Now we know the data as in the input audio and the transcription, right? How do we actually figure out to train a model from these 2 things? Well, it's not that easy, right? So the first thing you want to do is actually how do we process the input audio? And this is going to require some background in signal processing. I don't know if somebody has background in anything like that here. If not, that's okay. It's not really needed for the course, but usually if you're working on the feature extraction part of this pipeline, you're doing a lot of signal processing in this part, right? Because you're taking the audio frames, you're processing MFCC features. Essentially, these are like Fourier transforms. And then you have spectrogram features, which are also something similar. You have F-banks, which is a little bit more complicated. Essentially, the main idea is you want to extract some sort of feature representations for each audio that you input. Right, so you have like a frame level sort of audio alignment thing, right? So if you have an audio for 5 seconds, if you're speaking for 5 seconds, that usually would correspond to something like 5,000 frames in the input audio, right? Depending on how you actually process your features, that can change, but let's just go with that number for the rest of this tutorial. Okay, so you have 5 seconds of audio, you have 5,000 input frames, right? That's going to be your feature set. Now, what's the next step? Well, we got to figure out how do we actually process the input features using an acoustic model, okay? And even that part is going to be sort of this main speech recognizer block here in pink, but even that part has like multiple different moving parts to it. So let's go down here inside the speech recognizer, okay? Now, does everybody know what a sequence-to-sequence model is? It's pretty popular now, so I think people should know it by now, but back in the early 2010s, I think, I think before 2014, whenever the sequence-to-sequence paper came out, and even in the early 2000s, there was no sequence-to-sequence model, right? So we had a problem of basically, how do we take in a variable input sequence and then map it to a variable output sequence? That was essentially the problem. And one of the ways we dealt with that problem was this CTC loss function, which I'll explain. Let's actually talk about that first. Okay, so let's just say you have the input frames here. You have x1, x2, and all the way to xm here, right? Those are your input frames. Let's just say you have 5,000 of those. You have a 5-second audio recording. But in a 5-second audio recording, how many words do you think I'm going to speak? If you're really fast, you might say something like, CTC is the simplest speech recognition system available, blah, 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 and then, 5 seconds over, right? It's not that many words you can speak in 5 seconds, right? So what is the problem right off the bat here? If you just look at the top figure over here in this CTC model here, we have 5,000 different frames, but then the output is not that long. Does that make sense? What do I mean by that? Okay, you have 5,000 input frames for the audio. That's a 5-second audio clip. And in a 5-second audio clip, you're only speaking maybe 5 words or 10 words. Do we see what the problem is there? Okay, what's the problem here? Describe it in words what the actual problem is. If you just look at this figure, I think this figure should give you a good hint. So the blacks are basically the input frames, and the blues are going to be here the output tokens. So you have a sequence of 5,000 frames, so that's 5,000 different time steps. And then for each of those frames, you need to have a label. Right? If you're just transcribing, yeah. Yeah, okay, so good question, exactly. This is what I was hoping for. So yeah, again, the first thing we have to figure out is exactly how do we generate the text, right? We can generate the text one character at a time, we could do one word at a time, or we could do one phoneme at a time. Do we know what a phoneme is? A phoneme is basically just the actual, the noise a character makes if you say something like the nasal tone of the actual character or word. It's not used that much in speech recognition anymore because it's outdated now, but early, like back in the 80s and 90s, everybody used phonemes because they were more, I guess, useful as a feature, just to generate text. And then they would have a phoneme to actual word mapping that would actually give you the final transcription. But now that's a lot more simplified. We just use characters or words. Okay, so let's just go with characters in this case, okay? Let's just say we generate the text one character at a time. What is the problem then? You have 5,000 input frames, right? But you don't have 5,000 characters, right? The number of characters is going to be a lot smaller than that, right? And if you're doing words, it's going to be a lot less smaller than that. Okay, so then who can describe what the problem is? It's essentially what the sequence of sequence architecture actually solves. This is like what this model is known for. You have an encoder and you have a decoder. And the whole point of separating the encoder and the decoder is what exactly? Exactly, yes, different lengths, because you have a variable length input and it's not going to be guaranteed to have the same size as the output, right? That's exactly why sequence of sequence or encoder-decoder models became popular, right? Because you can now handle variable length sequences, right? So the input and the output don't have to have the same length anymore, which is really useful because now you can do like stuff across multiple domains, right? So speech recognition is just one simple example, but think about, if the encoder was a bunch of images in a video, right? And then the decoder was something like, well, give me a caption for the actual video, right? Same kind of problem there, except now instead of speech, you have video images. But then again, the caption is not going to be as long as the video is, in seconds or whatever it is, right? So that's kind of like a domain problem, which this model really solves really well, right? Because now we've separated the encoder and the decoder, okay? But before there, let's just go back to the CTC. This is just the motivation for the actual CTC, right? Before we didn't actually have this paradigm, we were trying to figure out, well, what do we do here, right? Because we have 5,000 frames, but we only have maybe 50 characters of text. How do we actually learn an alignment of the characters to the input frames? That was the problem, okay? And in speech recognition, even before that, actually, the older you go, the worse the problem actually becomes because we had very trivial techniques to actually solve this problem, right? But back in the 80s and 90s, the way they actually collected the data for speech recognition was really tedious because for every single input frame, the person who's collecting the data would have to mark if this was a character spoken at this frame or not, right? Now, if you collect data for speech recognition, it's a lot easier, right? You just speak something into the audio, you tell me what the transcription was, and we figure out exactly how the transcription actually matches to the audio, right? Where in the audio the actual transcription was spoken. But back in the days, we didn't actually have an alignment model, right? So there's no way to actually learn the alignment. So when we collected the data for training the model, basically people have to go in there and go for every single frame if there's a character spoken or a word spoken at that given frame, which is a really bad thing, right? Because it's like tenfold worse. Okay, so CTC essentially solves that problem, right? And the way it does that is in a couple of different steps. So the first thing it does is it allows for repetition. So you can allow repeating characters. And you can see why that makes sense, right? Because if I'm really saying something like in words, for example, if I say cat, maybe the C in the cat is going to be spread over a bunch of different frames. Maybe it's not just one frame, but it's like 5 or 10 different frames, right? Because you have 5,000 different frames, obviously, right? So it's more of sort of a, zooming in, zooming out problem. So CTC, the first thing you could do is basically allow for repetition of characters or words or whatever your token is. Second thing, you can actually introduce a blank token in there. So a blank token is going to be something like, well, nothing was really spoken at this point in the frame. It doesn't really make sense when I'm speaking really fast like this right now, but when you actually slow down the audio, it makes a lot more sense, right? Because I'm not going to say something at every single frame at that level. Okay? So two things, right? The vocabulary is now changed because you can have repetition, you can have a blank token. And then thirdly, which is the most important thing, which is the really cool novel innovation for this algorithm, was that the loss function actually computes like a marginalization of the alignments of the output text with the input frames. So essentially the loss takes care of the alignment problem and learns an alignment automatically, which is really cool back when I learned about this the first time, right? Because before that, again, like I said, the data was collected at a frame level basis and humans would actually go in there and annotate every single frame, which is a very bad problem, right? So this actually takes care of that. So if you train the model using the CTC loss function, the model actually learns a really good alignment of the input audio frames with the output characters, or whatever words or phonemes, whatever tokens you use. Okay, and this is actually still really useful because now when we go to the sequence or sequence paradigm, you have encoder-decoder models. This already allows for variable length input and output sequences. But even in this setting, the CTC loss is really useful for actually learning the alignment, which is a really cool thing because it uses essentially dynamic programming to figure out all the possible alignments of the output with the input, and then does a sum over that. So it's essentially just marginalizing out for all the possible alignments. Does that make sense? Kind of. It's a very hard thing to actually describe because there's a huge paper on this, and the loss function is not easy to compute because to even compute the loss function, you have to write like a dynamic programming implementation of the actual loss. So it's not that easy, but if somebody who's done Markov models or HMMs might know about dynamic programming a little bit, they might understand this paper better. So it's essentially motivated by that exact same sort of paradigm. Okay, so that's the CTC loss function. Now we have sequence to sequence. This makes it a lot easier because now we don't actually have to do anything with the input frames, right? We're not actually inputting the alignments. We're simply just giving you the input frames, giving it the transcription, and the model learns everything by itself. Okay, does that make sense? So if you just drop the CTC component out of this acoustic model, right? Right now we're just learning the acoustic model. What is one problem you can think of happening here? Or what's one thing that's not obvious from the sequence or sequence model? What's one thing that the CTC gives you? I already actually mentioned this, that the encoder-decoder model doesn't give you explicitly. It gives you the alignment, right? It gives you the alignment of where the actual characters were spoken corresponding to the input frames, right? So that's already explicitly there in the CTC model. In the encoder-decoder model, it's not explicitly there, but you can recover it somehow based on some sort of attention mechanism. And then you figure out where the probabilities are high for a given character corresponding. So you can do things like that, but in the CTC setup, it's quite explicit, which is a really good thing. Okay? So this is just part of the acoustic model, obviously, right? Again, we're just inside this pink block right now, speech recognizer. The acoustic model is just going to be trained usually using encoder-decoder models. You have this loss function here, which is just the negative log likelihood. And then usually you would also combine that with the CTC loss function to get like a mixture objective, which you can train the model with. And then once that's done, you basically have your acoustic model. Okay, that's just the model that processes the audio and then has some sort of latent representation for the audio input frames. Okay, what's the next step? So if I go to test time now, right, I just give you an input audio. How does the model actually generate the text for that audio? Well, the encoder-decoder model is pretty simple, right? Because you just encode the actual sequence here, and then you would decode the text, whatever characters or words that you're using, one step at a time, right? So what's the most simplest way of decoding a text model? So let's just say give you the input audio, and then if I'm doing transcriptions based on characters, let's just say we're outputting one character at a time, right? What is the simplest way to decode, in a model like that? Yeah. Yes, that's good, yes. But even before that, from the model, what do we get from the model? At every step of the decoder, what do we actually get from the model? If we get probabilities, that's right, right? How do we actually make the decision on what character it is? It's a very simple thing. You can just take the max probability, right? You can just take whatever token has the maximum probability. So that's called greedy search or greedy decoding, which is just basically taking the maximum probability at every step, and that gives you the characters for every word in the transcription. That's usually not that good because of various reasons which are hard to describe. But another thing you could do is use beam search. Have we talked about beam search in class? Yes? So beam search usually is a little bit more sophisticated because instead of taking the maximum probability for every single step, you are, excuse me, you're actually just you're generating the whole sequence one step at a time, right? Or maybe like if you have 1,000 different beams, you have 1,000 different sequences that you generate, and then you're looking at the total probability of each of those sequences. All right, so you're keeping track of the actual total probability for the generated sequence instead of just doing the max probability for a character level thing, which is, I think, a lot more useful. Okay, so that's part of the decoding process, right? If you have an encoder-decoder model, you could do that. But then the other thing that sort of is not that good with the decoder model is that if you usually just train the data on input audio and then output transcriptions, it's not going to learn a very good linguistic model or something known as a language model, right? Because you're only training on the transcriptions for the audio files. Okay, so one thing people usually do, and I think this is done by like every major, Google, Amazon, Alexa, speech recognition system out there, which is that they combine the decoder with some sort of a language model, which is trained on a lot more text data. So think about GPT-3 or one of these new models that can really generate a lot of text, right? And they can generate this text really nicely. It makes a lot more sense. And essentially what the decoding process here now is going to look like is that we'll generate the sequences of the decoder for the given audio, and then weigh the input sequences using a language model to see if that makes sense or not. Okay, so if you have a decoding from the actual acoustic model, let's just say, for a sentence like CTC is the simplest speech recognition system, right? But it gets a couple of characters here and there wrong, or maybe some of the words don't make sense. Okay, so for example, if I'm speaking here, right, if I say the word here, it could mean H-E-A-R or H-E-R-E, right? There's two different words. They mean two different things, but they sound exactly the same, right? So in an acoustic model, the model is not going to know how to differentiate between the two, right? So it's possible that the model actually outputs H-E-A-R, for example, when I really meant H-E-R-E, right? In that case, a language model really helps because the model can actually go in there and say, well, no, this doesn't actually make sense in this context. And in this context, it's more likely that H-E-R-E was really what's meant. Okay, so that's just a simple example, but there's a lot more things you can think about in language because language is obviously really complicated. It depends on how the person is speaking, and there's a lot of different moving parts in language. So usually you would have a linguistic model that's trained externally based on more data, and then you would combine that with a decoder when you're actually coming up with the transcriptions for the audio. Okay, this is how Google does it when you speak to Google, or even in Android Auto when you're speaking in the car, which is actually a lot tougher because there's a lot more noise in the background, right? So in a quiet room like this, it's a lot easier because I'm just saying something, you can hear it clearly. But for example, if you're driving on the highway, it's not going to be that simple, right? Because there's a lot more noise in the background, and so models are going to be thrown off a lot easier in that case. All right. There's ways to deal with that problem as well, but it's beyond the scope of this course. And if you're really interested, you can look at this notebook. I think it talks a little bit about that as well. Any questions about speech recognition in general? None of this is actually needed for the assignment, by the way. This is just for your interest, okay? Because this is really a cool problem and a cool domain. But the assignment actually simplifies a lot of this for you. So you're not actually implementing any speech recognition systems here. You're not even actually training a full model, I think. You're just training a model in question, let's just see, question 3, is it? Yeah, in question 3, you're training a model which basically is going to be a language model. So it's not even the full speech recognition system. It's not even the acoustic model. And acoustic models usually are very hard to train anyways because you need a lot of data to train the model. And it's just, we just don't have GPUs in the course, right? So actually have every single one of you train a model that big. Okay? But you'll be training a language model or like a mini language model in question 3, which is going to be part of the bigger pipeline for speech recognition. Okay? All right, so I'll go to questions for the assignment now. Any questions about the assignment? I can just go through questions one step at a time and then maybe just talk about them briefly and then let me know if there's any questions. That make sense? Okay, so question 2, really easy. Everybody should get 10 marks on this part. Okay, you can see I'm one of the head TAs here for this assignment. I don't want to get a lot of hate from you guys if you don't do well on this assignment. I heard there was a couple of issues with assignment 1 in the course, so hopefully it's not going to be as bad for assignment 3. I really don't think there's anything to worry about for assignment 3 if you just follow the instructions carefully. So question 2, who started the assignment, by the way? Who's not started? Okay, actually, who's not started the assignment yet? Okay, that's fine. It's okay. Maybe you should start reading the handout. It's not going to hurt if you just read the handout. Question 2 is really simple. Okay, so essentially you're just doing exactly what they're telling you here. You're recording yourself saying 10 different sentences. Okay, and you can follow one of these, specifications here. You can say like a word. You can say a sentence. You can say maybe a sentence with some repetition or some stuttering, something which is, has a different variation to it. Okay, so just maybe follow these guidelines. I think there's 9 different variations here, but you have to come up with 10 transcripts. Okay, so just do that. That shouldn't be that hard, right? Okay, so that's step 1. That's already most of the work for this question, believe it or not. And then step 2 is going to be figuring out how do we actually transcribe those input audio files. Now, for people who actually started this question, what did you guys use for this part, for step 2? Okay, good, very good. SpeechBrain. That's probably the easiest one you can use for this part. I wouldn't go with Kaldi or PyKaldi because these were really written back in the day, and this was like when people were using C++ a lot. They're not using that anymore because everybody's using Python for machine learning. And the bash scripts, they're not going to be that easy to understand. So I've seen these recipes, they're not that easy. I wouldn't use them. Okay, I would just go with SpeechBrain because it's literally just 3 lines of code. Okay, I'll show you exactly what those 3 lines look like, and nobody should have an excuse for getting less than 10 on this part. All right. So SpeechBrain, if you just go to the website for SpeechBrain, go to the tutorial section, SpeechBrain Basics, and I think if you just click on this one, what can I do with SpeechBrain? I have that open here. Essentially, it tells you exactly what you do for this question. Okay? It talks about some problems in general that SpeechBrain can tackle, and maybe you can look into this yourself if you're really interested. There's a lot here, obviously, but they're simplifying a lot of this for you. Right? The way they're simplifying is this, simply by these 3 lines here. You can just import the model that you want to use, okay, and load the model from the given checkpoint, whatever it is. So if you're using the Liberty Speech model, you would use this. You can also use a couple of other models if you want to. If you're really interested, try out a couple of different models and see how the transcriptions actually change. And then you would just call this, the 4th line here, transcribe file, on your given input file. That's it. That's basically it for question 2. Okay, so everybody should get 10 marks for this question. All right? Any questions? This one's fairly easy, guys. Don't mess this up. Okay, so use SpeechBrain, okay? Don't use anything else. I would get rid of all this for the next versions, next year's handout for the course. Okay. Question 3 is going to be, I think, perhaps the most challenging part of the assignment. It's not going to be that hard because we're basically giving you sort of the skeleton for the actual code base. So you're not actually implementing everything from scratch. You're just filling in some parts of the actual, classes and the functions. Okay. Any questions about this one? This one is going to be fairly obvious if you just read the paper. Okay. Just read the paper. Just make sure what they're saying makes sense to you, and then just implement it in whatever PyTorch. Right? Yes. Yes. Mm-hmm. Yes. Yes.
So this attention matrix we get by multiplying K transpose?
No, the attention mask you don't get. The attention mask is given to you.
The attention score.
Yes.
So when we apply this attention mask, it should be dimension 3 or dimension 4 because it depends. Are we masking out the?
Yeah, you tell me.
Or the key?
So you tell me. That's something you should figure out. Okay, so essentially there's 2 sequence lengths, right? In the scores, there's batch size, then there's, I forget what the second dimension is. Yeah, the number of heads, that's right, and then the sequence length, right? So you have to figure out exactly what that matrix represents. Just figure that out, and then you'll know which one to apply the mask to. But essentially the mask is already given to you in the right size. It's given to you in batch size, 1, and sequence length, so that should tell you already where you're applying that. Okay, Yes. For question 3? Sure, yes. Yeah, you can try a frozen one. I would really encourage you to try other hyperparameters. It really depends on what the final accuracy of your model looks like. So I know there's also a problem with this question about the flexible setting for question 3.2, which a lot of people couldn't actually get it to train with the flexible option on because of some memory constraints. I don't exactly know what's going on there. But even without the flexible option for 3.2, you should be able to get at least 80% accuracy. Okay, that's the number I would keep in mind without the flexible option, okay? So try out hyperparameters as much as you can. Try to change a couple of different things in the model here and there, and see if you can get 80% accuracy. I think that should be easily possible. Sorry? Yeah, 80% is the number I would aim for. Yes?
For the problem with the flexible,
yes.
you just need to request a GPU with more memory.
That's what I thought, because a lot of people were saying I had to just clean my disk space up, which doesn't make sense. The disk space has the...
I think there's two, sometimes you get the disk.
Okay, so
Sometimes.
Okay, so I think what's happening with the flexible option is that it's dumping too many artifacts during the training. So it's saving checkpoints or something else, which basically eats up your disk space. And also the GPU memory, I think that is also correct. So make sure if you're running this on a GPU on the teaching servers, just run srun with a GPU. I think you can do I forget what the actual option is for the memory, but you can specify the memory option in this command here. And make sure you get like 16 gigs of memory or something like that. Or just keep trying higher ones till you actually get the script to pass. I mean, it's not that hard. Yeah.
I wonder, like, really trying to experiment with kind of hyperparameter or anything, do it like just to maybe make a list about bunch of hyperparameter we use and see if this one has the best result. Do we need to have some actual explanation about why we choose this hyperparameter?
Yeah, so the way I would do this in the description in the file would be, I would just say if you did like a grid search over the hyperparameters, right? So does everybody know what a grid search is? Yes, a grid search is basically just different combinations of different hyperparameters, right? So if you have a hyperparameter alpha, which you're searching over 0, 0.1, all the way to 1, and then if you have a hyperparameter beta, which you're searching from 1 to all the way to 10, a grid search would just combine those different possibilities, right? So you just have like 10 times 10, for example, in that case. So I would just describe the hyperparameters in a grid search setting if that's what you did, and say I grid searched over these values for this parameter. That's going to be the description. And then you can also do one sentence talking about the best model. So you can say the best model which had this accuracy had these hyperparameters. Okay, so that's what I would do. I would do 2 steps like that. Yes?
So for a grid search, we basically retrain the model with each set of the hyperparameters.
That's right.
So in this case, we train it 100 times.
That's right. Well, yes, 10 times 10. That's right, exactly. Yeah.
How long?
But I'm not saying you have to do it 100 times, by the way. That's not, yeah, that's just an example, but you could do a lot smaller than that. You could do it like maybe 2 times 3 times 3, depending on whatever you're changing in the hyperparameters, right? So, okay, well, here's the question. What are the hyperparameters you can change in this file? There's some really simple ones. Sorry? Learning rate, batch size, exactly. The number of iterations you train for, maximum number of iterations. Right? If you just do a couple, like 3 or 4 of them, that should be more than enough, right? And even for the learning rate, you could just do like a grid search over like 3 or 4 different learning rates. That should be enough, I think. As long as you actually get the model to converge, that should be okay, right? If the model diverges, that's not a good thing because that means your learning rate was too high. Okay? And so yeah, if you want to get the 80% accuracy without the flexible option, you might want to try out a couple of different batch sizes and learning rates and see what works best in that case. Okay? So that answer your question? Make sense? Okay, good.
How long would you expect the model to train for this assignment? Like on
That's hard to say. Okay, so are you running on a GPU or just without the GPU? So on the teaching servers, for example. I don't know. For somebody else who's run the model, how long does it usually take for one run? It's not that bad. It's pretty good, yeah. Sounds about right. It's a mini BERT model anyways, right? So it's not meant to train the whole BERT because that would be like stupid number of months, which we don't have in the course. And we also don't have the compute power. So it's a very small model. You should be able to train it really fast and try out a bunch of different settings. Okay. If I were you, I would just run a script. I would just make a script with these different commands in there, srun, with the different hyperparameters specified at the command line. Okay, and I would just run that in a script all at once. So you could just run it once for like 1 or 2 days, and the script runs, you get all the different models. All right, and then you can look at which one the best one is. That's how you usually would do it in a research setting anyways. You would just run the hyperparameter search, because you don't want to keep running every single model after every single hyperparameter, because you have to check back in, right? It's not going to make much sense. So you can automate all of that, put that in a script, and then you can even put that script actually in the report.txt file, just to tell us exactly what you tried out. Okay, and you can even tell us the exact command you ran. So you just say, this was the command I ran for the best model tag. And that makes it easier for us, because if you really want to check your work, I'm not saying we're actually going to do it, but if you really want to check your work, if there's something suspicious about it, but we could just use the command and run the command and see what we get. Okay. All right. Any other questions? Yeah. Yes, validation. Yeah, we're never training. We're never looking at the training accuracy, anyways, right? Because that's going to be overfit anyways. Oh, okay. So then maybe try for the test set.
Test set isn't global. It's just all three.
Oh, then just do the validation set. Just do the validation set. That's what I thought. I mean, we were just reporting the validation accuracy anyways. I don't think you're supposed to run it on the test set anyways, because it's another overfitting problem essentially. So when you're training the models, you want to get the model with the best hyperparameters on the validation set, and then use those hyperparameters for the test set evaluation. With the test set, you never want to evaluate this more than once. Okay, so just you find the best set of hyperparameters on the validation set, and then use that for the test set evaluation. Because once you know the test set number, then you can actually overfit in your head as well, right? Because then you can say, well, let me see what gives you the best performance on the test set, but that's not correct, right? You should never do that in practice. Okay, questions? Okay, so 3.1, 3.2 should be fairly straightforward. It's just implementing the stuff. I can't tell you much here because I don't want to give you away the answer, but it's, just read the paper if you don't really understand some of the details, but it should be fairly easy. It's like most of the stuff is already set up for you. You can just read parts of the code and figure out exactly what needs to be done. Like, you mean, what are you going to submit here? Yeah, so for question 3, there's only one deliverable, right? This is the BERT report.txt. You're going to put everything in that file. So you'll tell us exactly the hyperparameters, what the grid search was, what was the tuning procedure, what was the accuracy for the best validation performance, the runtime, if you did use a GPU or not, and then you will submit the 2 files, classifier and BERT.py. So yeah, so whatever you want to put, you can put in the txt file. Okay? All right, so question 4 is language modeling stuff. Again, 20 marks, it's not going to be that hard, okay? 4.1 literally should be 5 marks for everybody who did 3.2, right? You're just going to run the model in 3.2, train the model, and then load that model for question 4.1. Okay, so question 4.1 is just going to simply, well, you have 5 sentences. You come up with 5 sentences randomly. Well, not randomly, actually. You should follow whatever has been said here. So just follow these specifications here. Right, so one which is very positive, very, very negative, something in the middle, and so on. So just do 5 variants according to what's been said here. And then you simply just want to query the model and see exactly what the sentiment is going to be. Right? In question 3.2, what are we training here? We're training a classifier, right? It's a binary classifier. It's going to say yes or no, or positive or negative, whatever you want to interpret this as. Right? And in 4.1, you just want to simply report what it actually says for each sentence you come up with. Right, so this is just validating, if the model is doing something remotely sane. Right? So if you have a positive sentence, it should say something like positive or yes or whatever. Yes, makes sense? Okay, so this one should be good, 5 marks. 4.2 might be a bit harder, but even that, it shouldn't be that hard, right? Because here, you're simply loading a model from the transformers repository here on Hugging Face. So if you just click on one of these links, it actually tells you exactly what needs to be done. Okay, if we just go from pre-trained, no, that's from pre-trained. Yeah, I think you would just use a pre-trained one. So we just have this line here, and I think you can use whatever we told you here, right? So BERT base on case. So use that model in the pre-trained, load the model, and then again query the model for the exact same 5 sentences in 4.1 and see exactly what it gives you. Okay, so this one is a bit harder because here you're using a causal language model, right? It's not going to be a classifier. It's not going to output binary yes or no. It's going to give you the probabilities for the next word of the sequence. Yeah? And so for this part, you just want to query the probabilities for the yes or no tokens and see what they look like. And that should give you some indication on what the polarity of the sentence is. So is it positive, negative? It should give you some indication on what the sentiment of the sentence is. So it's not a sentiment analysis model, but you could use a language model in some settings like that. Yeah.
I'm just wondering why we're using two yes and no tokens rather than positive and negative.
Yeah, I think it would be equivalent. I think we could just change the question to be positive or negative. You can actually put that in the discussion. That's a good thing to put. You could say, I was trying positive, negative, and the results also made sense in that setting, right? Because it is possible that the model reverses yes or no, right? So, for example, if I ask the question, was the movie review positive, right? If that's what the model is learning, it might say yes for a positive review and then no for a negative review. But if the question was the movie review negative, then it's going to say no for a positive review and then yes for the opposite. So it is possible yes or no could be interchanged. But in that case, you want to explain more, and then you could do something like, look at positive, negative, and see what those are. Right? So that's a really good comment, actually, yes. But I think for this model, I think yes or no should be, positive yes and no negative. Questions? Okay, this one should be good as well. Okay, 10 marks. It's easy. It's not that hard. Pre-trained model, you're just coming up with the sentences. Just tell me exactly what the yes/no probabilities are. It's a little bit of coding, right? Because you just want to make sure you're actually getting the logits out of the model, and then from the logits, you're going to get the probabilities for the yes or no, and then, well, it's only like 2 lines of code anyways, but you get the idea. It's not that hard. Okay, because the model outputs logits, right? So those are unnormalized log probabilities, and you want to get a probability from the model. It's like one step. It's just a 1 line of code. Yes.
In this case, why are we using yes and no and not words like positive and negative again?
Yeah, exactly. That was the question, right? And I mean, I guess the instructor came up with this assignment, so I don't really know what to say. But it's one of those things which it doesn't really matter what you use, as long as there's some sort of contrasting qualities. So yes or no, or positive, negative, or even like 0 or 1. Okay, so 10 marks, easy. Everybody's going to get perfect on the assignment so far, right? Yes? Okay, 4.3. 4.3 is 5 marks, and this one's also not that bad. This one is just going to be using one of these large-scale language models here. And in this case, the language model actually generates the text, right? So it generates the next word. It's not just giving you a probability, although I think you could do that with the API. The API also tells you what the probability is, but this is generation mode, right? So it's just going to continue writing for you whatever the sentence you left out was. So if you said, describe the movie, and then this movie review is, and then the text generation is going to kick in, and then maybe fill in the next couple of words. Now for this part, it's not always going to be the case that the text generation is going to say the movie review is positive or negative. It's possible it could say something else. Okay, it's possible it could say this movie review is interesting or something like that. Okay, in that case, you want to try out a couple of different variants and see how close you can get to like a positive or a negative thing. Or even if you don't get positive or negative, how close do you get to actually a sentiment, like where you can actually get a sentiment out of the text generation. Okay, so interesting would also be a sentiment. It's not as strong as a sentiment as positive or negative, but it's something better than, so it should be something like this movie review is, incomplete, for example, right? If that's the case, then you want to try again with a different variant of the sentence. Yeah, you can make that explicit if it really doesn't give you anything with this movie review is. But this sentence, this movie review is very weak, right? Because it's just saying fill in what the next word is. But if you ask it an explicit question like that, it might make it a little too easier. But if you say, is this movie positive or negative, even the most basic language models could say like one word at that point. So yeah, try to make it as hard as possible for the model. And if you can't get it, then you can always just say, well, I also tried this, asking this as a question, and then it said positive or negative. But be creative in this part, right? It's not, yeah.
So for the task 4.2, like we just need to get the distribution probability of the next word.
That's right. Generate a sentence or even a word. Yeah.
So like for 1.3, like how can I like judge whether it is better than the smaller model? Because like they are outputting different things.
Yeah, they output different things, but you can sort of make a comparison by looking at the so yes, 4.3. You look at the next word. I think in some of these APIs you can even get the probability of how likely that was, or like what the actual probability was before the model decided to generate that word. You could do something like that as well. But in general, a direct comparison is not possible, right? Because you're comparing probabilities to like a token, right? So you can only compare probabilities, which I think some of these APIs can give you if you really want to go that deep. But I don't think there's actually a comparison here, right? You could just say, well, is it better than the smaller model in the previous sections? Well, good question. Now, what is better going to mean in this context? Well, a classifier obviously is not going to be as good as a language model because a classifier is just going to be yes or no, binary prediction. A language model in generation is actually going to generate words for you, right? So how are you going to comment on the performance of the models? Okay. It's not that straightforward. I mean, okay, no, not straight. It's not that hard, but it's not obvious what the comparison should look like, right? Okay, so for example, if the API that you use here in 4.3 gives you something like this, movie review is incomplete, and then the classifier from the previous section, 4.1 and 4.2, for that exact same sentence give you something else like positive or negative, and then you have to really go look back at the sentence and say, was it really that strongly positive or negative? And then does that even make sense in this for the sentence or not? And then judge based on that. So it's not really a quantitative comparison, it's more like a qualitative thing, right? You judge based on the quality of the sentence, and then based on what you feel the sentiment should be for that given sentence. Does that make sense? You can also compare probabilities. You could do that, but that's going to be a little bit more work. I think with GPT-3, I think it might be possible to get probabilities. I don't know because I haven't actually tried this myself. Has anybody else tried 4.3 yet? Can you get probabilities for the generation? You can, right? Yeah. I think it's possible. So you can compare probabilities, but it's not meant to be comparing probabilities anyways. That was part of the question. So go back, look at the sentences, and then decide if it should be positive or negative or something in between. So what I'm saying is you should know the true answer in that case. You should know if a sentence is really positive or really negative or somewhere in between, right? You're deciding that. Okay, yes. Questions?
So I just need to like mention whether a sentence like the generate sentence for 4.3 is really positive or not.
Well, you would do that at the start of this question, right? At the start of the question, you come up with 5 sentences, right? And then you would say, this is a positive sentence, this is a really negative sentence, this is one which is in between, and so on, right? You would describe that. So that's kind of like the ground truth in this case, right? And then 4.1, you compare the probabilities, 4.3, you get the generation, and then based on that, you make your judgment on whether it's better or not. Yeah. Yeah, but you want to give some sort of explanation. So if you just say it's better, it's not going to answer the question because part of the question is, what does it mean to be better in this case? You have to explain what do you really mean by that. Okay. Okay, any other questions? Okay, question 5 is 1 mark. That's a free mark. Just make sure you give some feedback on the assignment. Question 6 is going to be a bonus question. Again, I think there's a lot of components here. You can actually do a lot of these. But we have a maximum of 10 marks, so we can do at most 2 questions from here. The tutorial next week by Shuja is going to be on 6.2. So that's going to be looking at the model explanation using this SHAP or shape thing. I don't know how to say it. But essentially, you just want to go to the documentation here, right? Look at one of these notebooks here. Just try out the examples. Try out a different model. Try out some different data. Okay? See if you can do some interesting things there, and then just report exactly what's been done in the notebook. So machine translation is an example. I don't know if you guys talked about machine translation in class. Did you talk about this in class? Machine translation? Yeah, okay. So you can do that as an example. You don't have to do exactly this one. But essentially, it's some sort of an explanation on what the model is actually doing. Are you trying to explain what the model actually meant to do when it was doing this? All right? You can also try like different data here, see if you can confuse the model a little bit, throw the model off a little bit, and see what the result there in that case is. And then comment about, is the model really good, really robust to like noise, robust to input perturbations? Some sort of an insightful comment, right? It's got to be something that which makes sense and something that helps describe what the actual model is doing. Okay, so that's going to be the tutorial next week. Again, this is like really simple, so you guys can do this yourselves anyways. You don't have to wait for the tutorial next week. You just take one of these notebooks and just edit one of them. Okay. Any other questions? Assignment. Okay, we're hoping everybody does really well on this assignment, by the way. So I don't want to get a bad reputation for this assignment. So make sure everybody does really well. Okay, if not, that's it. Good luck for the assignment.